Thank you very much for the kind invitation and the introduction. So, the short outline of my talk is the following. After some introduction and motivation, I will just highlight three related results from our work. The first one is the so-called biochemical realization of dynamical models. Then bio-inspired feedback design using these models. And the final point is the modeling of traffic flows by reaction networks. So I graduated as a computer science engineer at the University of Pannonia. And we know that that course was already founded by Professor Roska. My background in the PhD work is nonlinear process control, and I started teaching at the faculty in 2001, so right in the beginning. I was a teaching assistant in linear algebra. And I'm a full-time member of the faculty since 2013. And the two returning elements of our discussions with Professor Roska were the following. The first one was the encouragement of bio-inspired engineering and computing. So he used to tell me, let's put your very nice equations into action. And the second one was the sharing of preferably all the research work with students. So, as a control engineer, I think in dynamical models. So these models are for describing the relations of quantities changing in time or in space or in both. These processes or models are everywhere in nature, technology, and everyday life. And of course, we need quantitative models to study and use and develop our knowledge related to these processes. This small example is shows some time-varying quantities of an epidemic wave. So with the blue line, we can see the epidemic wave, the proportion of infected people. The red shows the proportion of susceptible, and the green shows the proportion of recovered. So it is a normal flu epidemic wave. And our usual goals with using these models is understanding what's going on, deep understanding, prediction, what will happen in the future, and if we have the possibility influencing the process, which is called control. So this slide shows the quantitative model of an epidemic wave. I cannot go into the details, so we have a mathematical model, differential equations. I won't have more equations in the slides, but the most important thing is that such an epidemic wave can be expressed formally with a set of chemical reactions. So we assign material species to individuals. So this first reaction shows that when a susceptible and an infected meets, with some probability the susceptible will get infected and we gain two infected. So this is a second order reaction. And the healing process is a first order reaction, which means that after some time the infected will recover. And this is not a chemical process, this is a population dynamical model formally described by a set of chemical reactions. And in our applications, we usually work in the field of so-called non-negative or positive systems, this means that our quantities are non-negative. So from physical, chemical processes, if we have temperatures, concentrations, densities, numbers of items in population dynamical models, these should be non-negative. And this is a special class of systems. And we know that most of these models can be formally described as a set of chemical reactions, which is a model class which is general enough, but still easy to treat in a computational way. So we can say that this can be a biochemically inspired representation of dynamical models. And by the way, we know from mathematics that this is a universal descriptor of nonlinear dynamics. Okay, let's reverse the problem. And we have worked quite a lot in this field. Let us assume that we measure the quantities. We fit some mathematical model. First, let's assume that the fit is perfect. And the question is, can we determine the network which produced the data? And there were very few results in the literature in this field. And relating this to circuit theory, it's similar, of course mathematically different, but similar to finding an electrical network realizing a transfer function. The difference is that we have a general nonlinear dynamics here. And we know that the solution is generally non-unique, which means that many different networks can produce exactly the same behavior. It's not surprising, even from linear systems theory. And in this field, we define the so-called dense and sparse realizations of nonlinear dynamical systems. In the literature, almost everyone was searching for sparse realizations because these are minimally parameterized. And as a byproduct, we proposed the dense realizations, which contain the maximum number of transformations, which is mathematically possible. And it turned out that they are much more useful and interesting than the sparse one, because it can be proved that they give a unique superstructure which contains all mathematically possible networks that are compatible with the dynamics. So this is the dense realization of the epidemic model, and you can see that the original one is a subgraph. But we have many other possibilities, at least mathematically. And if we have many structures, then we can find preferred or practically feasible or useful or just interesting structures from these. And if we play with the realizations, then this will lead us to bio-inspired control design, which means that we have a system operator, a process to be controlled, and we would like to transform it through feedback to a nice molecular network mathematically. So the original process is not necessarily a chemical one. It can be almost any nonlinear dynamics, but the closed loop system will behave as a nice, stable, robust molecular network. And we know many theoretical conditions for nice behavior from the literature, and we have the realizations. And this is generally, this idea is called the feedback equivalence problem in control. So this is the feedback equivalence problem to a nice molecular system. What is it good for? To tell you the truth, we were not too much interested in that when we were developing the theory. But then came the COVID epidemic. And so this feedback principle could be applied for the inversion of the disease dynamics. So the problem statement is the following. We only observe hospital data because we do not trust other measurements. And the main task is to compute the transmission rate, which is the transmission rate which can produce this measured observed hospital data. And system inversion can be traced back to feedback control, and we were quite successful in computing the transmission rate, and from the transmission rate we could determine quite a lot of non-measurable quantities. This is just one result from the several. So an estimation of the underdetection during the epidemics. So from the hospital data, we computed the transmission rate. From the transmission rate, we could compute the state variables, so the compartments in the model. And immediately, we were able to say something about the possible underdetection of COVID. According to our computations, it was around 3.5-fold during the first waves, then 4.5-fold, and when the Omicron appeared, it more than 9, at least 9. And these results matched quite well to other results computed very much later using traditional statistical methods. The last result is a recent one. This is from this year. And in one sentence, we can say that traffic flow models are also reaction networks. What is the principle behind them? Let us divide a road into sections called cells or compartments. Usually these are a few hundred meters long, these sections. And what is the reaction in such a model? The reaction is the transmission of one vehicle from one cell to the next cell. So this is the discrete event. What is needed for this reaction? We need space in the next cell, and we need a car in the current cell. And after the reaction, we will get a new car in the next cell and a new unit of space in the previous cell. That is the principle. So the molecules are vehicles and units of empty space, and we proved that the mathematical model obtained from this principle is convergent to the solution of the partial differential equation, which is known for modeling such road sections, and not just road sections, but traffic networks as well. And this has quite important consequences and applications because we can use all the machinery of chemical reaction network theory to transportation. Okay, so finally, I think the most important fruits of our work are graduated students and first of all graduated PhD students. And on these topics in our group, there are 8 graduated students, and as far as I know, all of them are quite successful in academic research, industrial research, and teaching. Finally, I would like to express my gratitude, first of all, to Professor Tamás Roska for the invitation and for the opportunity to work at the faculty, and also to the leaders of the faculty and the university, all the colleagues at the faculty, and all the students, co-authors, and collaborators. So thank you very much.